Hello class, this is a continuation on further trigonometric identities part 1, and in this video we're going to look to apply these identities that we've gone over into a few problems involving the utilization of identities. I've actually put a little mini cheat sheet here for me and for you also, so it'll assist you in memorizing these identities. So let's get straight to it and do some of these examples. Here we go. So let's simplify the following expressions. Sine of 90 minus theta. Well, if you look at the first identity that we have there, well, sine of 90 minus theta, even though this is sine equals cosine of this angle, it applies also with the cos of this angle, so the reverse of this. So this is the same as cosine of theta. That there is a simpler expression than what the question gives us. Let's move right along. As you can see, there's two applications of this. So with this one, this is going to be, well, cos of the complement. Well, the cos of the complement in this one is the same as sine of that angle. So this is sine of phi over, if we do the same for sine in this example, this is the same as cosine of phi. And as you can see from our from our tangent identity, this is the same as tan of phi. Moving right along. This one I actually haven't written here because this is a reciprocal identity. So sec squared theta is the same as, that's 1, actually I'm going to write it like this, 1 on, or 1 divided by, well, sec squared theta is 1 on, sorry, not sine, cosine squared theta. Well, if we're dividing by a fraction, that's the same as 1 times cosine squared on 1. Well, that's just cosine squared theta. Oops, should move this over here. 1 on cos squared, oh, I can't get this to, there we go. 1 on cos squared theta over 1 on sine squared theta. Well, we're going to be using this identity. Let's take a look. If I move cosine to the other side, we get, let me write it in so we can see it. If I subtract cosine squared on both sides, this will cancel, leaving us with sine squared theta. So the numerator, this one, is just equal to sine squared theta. If we do the same to the denominator, I'm going to subtract sine squared theta on this side, cancelling this. I'm going to subtract sine squared theta on this side as well, leaving us with this expression. But that expression is equal to cos squared theta. So this is just cos squared theta. Well, as we've seen, this is the tangent identity, and that is equal to just, well, sorry, sine squared theta on cos squared theta is just tan theta, but because they're both squared, this is equal to tan squared theta. Let me bring along my little cheat sheet here. These identities are slightly more difficult in that we need to prove that the left-hand side is equal to the right-hand side. And we accomplish this by utilizing trig identities. So let's get straight to one example. You can go ahead and pause the video at any time you like. You can fast forward as well if you'd like to skip to the solutions. But I'm going to demonstrate that to you right now. Here we go. For this, I often only work with just the left-hand side. until it becomes the right hand side. So for this, I'm going to expand the bracket. So 1 times 1. So the left hand side is 1. 1 times sine squared a. Plus 1 times sine a is sine a. Negative sine a times 1 is negative sine a. Negative sine a times positive sine a is negative sine squared a. These two in the center cancel, leaving us with 1 minus sine squared theta. And as we've seen before, 1 minus sine squared theta is the result of taking the Pythagorean identity and moving this to the other side. So this is actually equal to just cos squared theta. And because we have this, we've proven that this is equal to the right hand side. End of proof. Let's move right along. So once again, we need to prove that the left hand side is equal to the right hand side. So I'm just going to work with just the left here. I mean, you could try work with the right hand side to make it look like the left hand side, but I often just work from left to right. So let's work with just the left. To think about this, notice how we only have sine squared theta on the right hand side. So because of this, this kind of indicates to me that we don't want cos squared in here. So let's find an identity to remove cos squared. Cos squared here, if we move this to the other side, it'll become cos squared equals 1 minus sine squared. That's what I'm going to be substituting. Cos squared is equal to 1 minus sine squared. So this is going to become 1 minus sine squared x minus sine squared x. If we collect like terms, this will be 1 minus 2 sine squared x, which is equal to the right hand side. End of proof. Let's move right along to the next example. Let's move these down. Once again, proving that the left hand side is equal to the right hand side. It's pretty tricky to look at where the left hand side is, but here's the equal sign. So we want all of this to eventually equal 1. Now a little trick that I found for this is it's difficult working with tan and cot. So I express everything in terms of sine and cos. So tan squared, using the tangent identity, tan squared is equal to, if we substitute this, tan becomes sine squared phi on cos squared phi. That's times what's remaining here. So that's going to be cos squared phi. Cot is the reciprocal of tan. So because of that, cot becomes cos squared phi on sine squared phi times this remaining expression here, sine squared phi is equal, we don't know if it's equal 1 yet, so we can't say it's equal. Notice how we have a denominator and numerator that can cancel each other, so let's cancel those. Likewise here, we can cancel those. That leaves us with sine squared and cos squared. So let's write that down. Sine squared phi plus cos squared phi. Well, that is the trigonometric, the Pythagorean identity. So this is equal to 1, which is equal to the right hand side. End of proof. One more example. In an example such as this, whenever you notice that there's a power that's higher here, a good little trick to do is we factorize this. So I'm going to take, well, there's 4 cosines here and 2 in this expression. So I'm going to take out cos squared b outside. So if this had 4 and we took 2 away, this leaves us with cos squared b plus, this one had only 2, so we got rid of all of them. This leaves us with sine squared, oops, sorry, that should have been b, sine squared b. Okay, so that's the left hand side, equal. But notice cos squared b plus sine squared b, that's just a rearrangement of the Pythagorean identity. So this is equal to really cos squared b times 1, which is just cos squared b, which is equal to the right hand side. That's the end of that proof. So I hope that gave you an insight into how we can utilize the various identities in problems. Hope to see you in the next video. Best of luck.